Okay, in this video we're going to be discussing blackbody radiation and also the radiation curve and something known as the UV catastrophe. First off, what is a black body? Well, a black body is an idealized body that can absorb all radiation and can also emit all radiation. So imagine you have a box or a cavity that has charcoal all within the walls of that box. So here's my box with the charcoal all lined up in here, which makes a perfect absorber. Then let's say we send a beam of light into this box, so this tiny little hole here. And as it hits the walls, it reflects, and some of this energy is absorbed by the walls. And eventually it keeps on reflecting, hitting the walls, around and around and around and around. And eventually, after numerous reflections, all the radiated energy will be basically absorbed by these charcoal walls. And this is what we would consider a black body. And an ideal body, black body, will not only absorb all the radiation that strikes it, but it will also radiate outwards all the radiation as well. In fact, every object, even at ordinary temperatures, radiates electromagnetic waves. You may even also realize that the temperature of that body is related to the color that you see. Maybe you've heard of something called like red hot, like a red hot iron. When you get something that's red hot iron, it's basically radiating this color, orangish red frequencies, and that correlates to a sort of a certain temperature. You think back to the days when you were using like Bunsen burners, and if you change the color of the flame, you got different temperatures. Or maybe you've even heard about like white hot, like an incandescent bulb. That's even higher amount of energy that's coming out per unit time because it's actually radiating all the frequencies of light. In class, I'll show you a little device that we have. Maybe you even have it at home called an infrared thermometer. The way it works, it registers the incoming wavelength of the light. So you point it at something like the wall, and suddenly it picks up exactly the temperature of that body that you're pointing at. That's an application of what we've been talking about. So this brings us to the black body radiation curve that you can see over here. This curve, this experimental curve, or this experimental evidence, couldn't be explained by classical theory. And so that's what we're going to discuss now. So there's two typical graphs that you could see. You could either have intensity over here plotted with respect to wavelength, or you could have something like intensity plotted with frequency. You see, in classical theory, if we talk about, say, the intensity versus the frequency, classical theory predicted that at higher and higher frequencies, you would get more and more intensity being emitted. And so the curve would look something like this, classically. Or if you plot like intensity versus wavelength, then what we would get something like this. So the curve would go around, up here, and then it would be basically continuing on, up here. So at higher and higher frequencies or lower and lower wavelengths, you get more and more radiated energy, and you basically end up with like an infinite amount of energy being emitted. That means like this black body here, which is a perfect absorber and emitter, that you're kind of just stick your eye right here and look at the light that would be coming out, it'll like burn off your eye. That's impossible. That wouldn't happen. You don't get an infinite amount of energy that's just coming out of that black body. So obviously that doesn't happen. And this is where it was dubbed the UV catastrophe, the ultraviolet catastrophe. So it's impossible to have like at higher and higher frequencies. This it looks like a quadratic here. It doesn't continue onwards. This is what doesn't happen actually. What really happens is as it goes up to here, it reaches sort of a peak value, and then suddenly it drops down to zero. And this is what happens in reality. So again, classical physics thought that basically at shorter and shorter wavelengths, that it was skyrocket off here, and you get infinite amounts of energy being emitted, and doesn't happen. You actually end up with this sort of peak wavelength or peak frequency, and suddenly it drops off. And this graph here, this black body radiation curve, couldn't be explained by classical physics. And you may notice also in the same graph here that when you look at different temperature curves, let's say you look at this one, this curve right here at 4,000 Kelvin. Here's the curve right here. It goes like this. So it's much lower here. And you can see that its peak wavelength right here is at 724 nanometers. But then if you look at like something like 5,000 Kelvin, then you can see the curve changes like this. And suddenly the peak wavelength now is 580 nanometers. So and it shifts a little bit over here to the left. Now it's kind of like this yellowish green area. Or let's say the temperature was at like 6,000 Kelvin, and then that you get this other curve right here, and again the wavelength shifts over to the left, further to the left here. Now at 483 nanometers, you get this sort of bluish color here. So hopefully you'll note that basically at higher and higher temperatures, the wavelength shifts over to the left. You get lower wavelengths or higher frequencies. And this graph couldn't, this idea, this temperatures here, couldn't be explained by classical theory as well. So when you think of like physicists, you think of typically we have kind of experimental physicists who are trying to fit some theoretical formula to this, and then we have theoretical physicists that are trying to fit a theory to this. So at the time, we had scientists that were experimental scientists that were trying to fit some formula to it, and it was a scientist by the name of Wien here who determined that there was a relationship between this peak wavelength that you see at 483 nanometers or 580 nanometers or 724 nanometers and it being related somehow to the temperature in Kelvin and some number here. So at higher temperatures, the peak wavelength shifted to a longer wavelength or a higher frequency, and it was related by this formula, Wien's formula. It was chemists and metallurgists and astronomers that could use this formula, but when they were using it, I mean, it couldn't be explained by classical theory. So we really needed another theory to come around. So we need to kind of explain this. And this is where Max Planck comes in here. Max Planck. This German scientist found a mathematical formula, which you can see written down here, or mathematical expression that basically fit this blackbody radiation curve. And we say he basically made this assumption that light comes in bundles of energy, discrete amounts of energy, which is equal to h times f. H is Planck's constant, very, very small number, as you can see here, measured in joules times second, and then f is the frequency of the light in hertz. So Planck proposed that atoms do not emit or absorb light continuously, but they do it in chunks and packets or bundles of energy, which he coined quanta, plural, or for singular, quantum. This revolutionary idea brought forth the field of quantum physics, that you think of basically light as being bundles or packets of energy and not as continuous wave. Alright, I'll save the discussion of quantization and what are photons and how does Einstein come into this picture in the next video.